Hi and welcome to this look at some acid-base exam questions. So we're going to have a look at some various topics. First topic is going to be a 5-marker using pKa values to calculate the pH of two different acids. So it asks you first of all to explain why the pH values are different between hydrochloric acid and chloric 1 acid. So the clue is in the fact that chloric 1 acid has a pKa value of 7.43. Whenever they do that, that means that that's going to be a weak acid. So what you do is you make these kind of points. It's a strong acid for HCl. It dissociates completely. You can put in the equation for its dissociation, for example, with the arrow showing that it shifts entirely to the right. Or you could say that the concentration of protons is the same as the original concentration of undissociated acid. By contrast, for chloric 1 acid, it's weak. It dissociates partially. You need to put the fact that it's in equilibrium in, if you put an equation, and the H plus ions, the protons that are dissociated, their concentration is much less than that of the original weak acid. So not every single one of these points are required, but definitely you need to include at least one of each for each acid to show that you're thinking about how they're different or why the pH values are different. So to calculate the pH value of hydrochloric acid, all you have to do is go and visit the concentration of the original acid, and because we've already worked out that the proton concentration is the same as the original strong acid concentration, you just plug it into pH equals minus log H plus, which gives you 0.85. Now chloric acid has a pKa value provided, and that, like we said earlier, that means it behaves as a weak acid. So you have to get the Ka value by doing 10 to the minus pKa. So that gives you 3.72 times 10 to the minus 8. Now I'm going to skip a couple of steps here. Normally you might write out the Ka expression, but we've already done a bit of describing in blue as to why the pH values are different, and it's 5 marks in total. So the key things are what I'm going to put in here. So the H plus ion concentration is what we're after, so that we can plug the H plus ion concentration for chloric 1 acid into pH equals minus log H plus. So to isolate that, you take the square root of the Ka times the concentration of HClO. So I'm assuming that you would know to get this from the Ka expression. That gives us 5.2, and ... means that it's a shortened version, so it's truncated. So I'm using the calculator value. So I'd plug that calculator value into pH equals minus log H plus, which gives me 4.14 with 2 decimal places. Notice 2 decimal places is the standard way of expressing pH values. So that's where our 5 marks come from. Let's have a look at the mark scheme to double check. And we've got HCl as a strong acid and HCl as a weak acid. They allow equations. So if there's an alternative answer, for example, to the 4.14, there's some ECF credit available down here. So calculating the Ka is our first step there. Working out the H plus concentration is the second step, and then 4.14 with 2 dP required. And you can see the same thing going on up here with the pH of the HCl, 2 dP required. The next question is constructing an acid-base equation. They want the full anionic equation. So I'll take you through what recall is needed to build this up. Firstly, a metal plus an acid will always give us salt plus hydrogen gas. So applying that to this particular version here, it's aluminium plus ethanoic acid gives you aluminium ethanoate plus hydrogen gas. So I'm putting the unbalanced equation because I need to take a moment to explain why there's a 3 here. And that's because aluminium is in group 3 and therefore forms 3 plus ions. You'll see that the ethanoate ion is 1 minus. So you need 3 1 minuses to match 1 3 plus. So that means that you put a 3 in front of the ethanoic acid. Now let's explore why it's 1.5 H2. Well, if you take 3 ethanoic acids on the left-hand side of the equation, it's this hydrogen here where I've put my highlighter, which will actually dissociate. If you've got 3 of them, that means 3 H pluses will dissociate from 3 moles 3 moles of H plus will dissociate from 3 moles of ethanoic acid. That would lead to 1.5 moles of hydrogen gas. So that's what you put up at the top. So now let's construct the ionic equation. So the first thing to do is to split all the aqueous species, your ethanoic acid and your aluminium ethanoate in this case, into their ions. You cancel out anything comparing on both sides, so that's the ethanoate ion, all 3 of them on both sides, and whatever is left behind, you use that to construct your ionic equation, and you include state symbols. So we put that up at the top as well. So doing a quick mark scheme check on this one. On the right hand side, I've highlighted where we got the marks. So either the doubling up or the normal one here is acceptable. They didn't ask for state symbols, but I included them because it's good practice and it's very easy to forget or not notice when you're being asked. So my advice would be, where possible, put them in. The final question we're going to look at is using Kw to calculate the pH of a strong base. So it's 2 marks and they want you to calculate the pH of 0.4 mole per decimeter cubed solution of sodium hydroxide. So where do you start? Well, the ionic product of water is a good place to begin because that's found on the data sheet. So there's a few things you need to think about first of all. Sodium hydroxide is a strong base, so it'll completely dissociate into Na plus and OH minus. That means the equation will be written as such with an arrow pointing to the right, so total dissociation there, meaning, like before with the strong acid version we looked at, that the concentration of original sodium hydroxide is going to be the same as the concentration of OH minus ions. So what connects them is the Kw. So to work out the pH, we need to isolate H+. So plugging in the numbers that were given, that means we divide 1 times 10 to the minus 14 by 0.4. And that gives us 2.5 times 10 to the minus 14 moles per decimeter cubed as our hydrogen ion concentration. So plugging that into the pH calculation like before, that gives us 13.60. And obviously this is what you'd expect for a strong base. You wouldn't expect a low pH, you'd expect quite a high pH. So it's looking okay so far. So quickly checking the mark scheme, we can see that we've got 2.5 times 10 to the minus 14, and we've done 13.6. Now I put it in as 13.60 because it's 2 decimal places. In this particular mark scheme, they didn't ask or demand 2 decimal places, but like I said before with state symbols, always put in 2 decimal places for pH, just to be on the safe side. Okay, hopefully that's been a useful look at a selection of acid-based questions. As always, thanks for listening. Until next time, see you soon.